Okay, you're given this polar equation. There's a graph in red over here, and you're asked to find out all points where this graph has horizontal tangent lines. Before we take a look at that, uh, here is that graph on Desmos. And let me get rid of some of this stuff right here. I wanted you to see how we could actually trace, how this graph gets traced out. So let me get rid of those horizontal tangent lines. And one more. And if I use this variable k to graph the same polar equation, but we can see it getting traced out. And so there it is as we approach pi over 2. And now as we go into the second quadrant, we go up this way. So the entire graph gets traced out when theta is between 0 and pi. You don't really need to go all the way to 2 pi. Okay. Another thing I thought we'd take a look at is that it's possible to come up with a graph that shows all the tangent lines to the curve based on this value of z. So there's a tangent line. These are all tangent lines. Let me label the point of tangency. So we're only finding the points where the tangent line is horizontal, but you could find tangent lines at any point on the curve. Okay, so I'm going to stop sharing and we'll talk about how you actually find dy dx, which is formula for slopes of tangent lines to this curve. So this is what we want to do. And we're going to use the fact that x equals r cosine theta and y equals r sine theta. These are the rectangular coordinates. These are the polar coordinates. So if we want to find dy d theta, we can put dy dx, we can put dy d theta over dx d theta, kind of picture these d thetas canceling out. So dx d theta would be using implicit differentiation on this. And we have to use the product rule here. So the derivative of the first times the second plus the second times the derivative of the first. And the same for dy d theta. There's a formula for dy dx in terms of theta. So that's the formula we're going to use. So my suggestion is to rewrite this as cosine squared is 1 minus sine squared. Distribute the 6 sine theta. There's another formula for r. So dr d theta is 6 cosine theta minus 18 sine squared theta. That's from the chain rule, derivative of the inside. And just to reiterate, we're going to use this formula. So there's the formula for dy dx. If we substitute in this value for r and this value for dr d theta into that formula for dy dx. So that's what it looks like. And we want to know, when does this equal 0? So that equals 0 when the numerator equals 0. So here's the numerator simplified in a couple steps. And if I factor out the 12 sine theta cosine theta and leave this binomial, that's going to equal 0 when sine theta equals 0 or cosine theta equals 0 or 1 minus 2 sine squared theta equals 0. So if sine theta equals 0, theta equals 0. If cosine theta equals 0, theta equals pi over 2, on the interval from 0 to pi. I could change this to pi. We'll talk about going to 2 pi in a minute. And or sine squared theta equals 1/2, sine theta equals plus or minus the square root of 1/2, or radical 2 over 2. So theta equals pi over 4, 3 pi over 4, if we take the inverse sine of radical 2 over 2. If we take the inverse sine of negative radical 2 over 2, we'll be in the third and fourth quadrants. So we think that these are our candidates: 0, pi over 2, and these two guys. So let's go to the next board. So if theta sub 1 equals inverse sine of radical 2 over 2, that's actually pi over 4. And if theta equals pi over 4, the radius at that point is 2.12. And so the x-coordinate of the point of tangency is r1 cosine theta 1, and the y-coordinate r1 sine of theta 1. So there's the point right there. And here's the line y equals x, or the tangent of pi over 4x. So the point is that is one of the points, angles, where the point of tangency has a slope of 0. And likewise over here, theta 2 equals 3 pi over 4, same deal. What we want to mention here is, here's dy dx again. Why doesn't pi over 2 work? Well, the reason is because pi over 2 substituted for theta gives us 0 in the denominator. So the slope isn't really 0. It's actually, looks like it's either positive infinity or negative infinity, depending on which side of pi over 2 you're coming in from. Okay, and here's how you can actually show the tangent lines. This is the equation for a tangent line where g of v is the formula for r, and then g of v times the sine gives you the y-coordinate. Here's the derivative, which is the slope, x minus the x-coordinate of the point of tangency. So that's what all of these guys are right here. And I will mention that if we continue rotating past pi, that we could end up at this point again, but that means that r was a negative value, because we'll actually be rotate down to here, and then r will be negative, and that takes us back to here. So there are some additional points if you let r be negative, but it's actually the same location on the curve. Okay, there you go. Hope that helped. If you have any questions, post a comment.